In this video, we will talk about the preparation of alkyl halides. We talked about the structure of alkyl halides before, and we talked also about the nomenclature. So a very important structural feature of alkyl halides is their electrophilicity. The fact that carbon that's directly bonded to X is electrophilic, and this is because of inductive effect caused by the difference in negativities between carbon and X. Therefore, the CX bond is polar. This polarity of the CX bond is very, very important in the chemistry of alkyl halides. In this lecture, we will discuss methods or preparation methods of alkyl halides, and we begin with the first method, which is radical halogenation or radical substitution. When we say radical substitution, we refer here to radical substitution of alkanes. So alkanes can undergo radical halogenation to make, of course, in the presence of halogen and light, to make an alkyl halide. So if you take methane, very simply, if you take methane and you react methane with chlorine in the presence of light, H nu, not HV, H nu, this is the energy, H nu, where H is Planck's constant, obviously, nu is the frequency, not velocity. H nu is the energy of light, if you like. We can say simply, you can write simply light, yeah. So it's light-induced radical substitution of an alkane. In this case, chloromethane is produced plus HCl. Yeah, we discussed this before. There is a lot of discussion here. This radical reaction, it begins with the initiation steps where the chlorine bond, or generally the XX bond, is broken homolytically to make radicals, and then the chain reactions take place, the propagation steps, if you like, until the reaction is finished or ends with termination steps. We discussed that mechanism before. So methane can undergo a chlorination reaction with chlorine in the presence of light to make chloromethane. No reaction should be observed or will be observed if there is no light or in the absence of light. Light is extremely important. It is essential in the reaction because it breaks the CL-CL bond or the XX bond in general homolytically, as mentioned, to make radicals. If we take ethane, the next alkane, this is ethane, CH3, and if you do the same reaction, so plus chlorine in the presence of H nu, in the presence of H nu, chloroethane is produced. So chloroethane is produced plus HCl as a byproduct. All right. Now, if propane reacts with chlorine now, and I use the skeletal drawing this time for simplicity, so propane plus chlorine in the presence of light, so we should, or we expect to get two products this time, because there are two different types of hydrogens. These three hydrogens on carbon 1 and these three hydrogens on carbon 3 or carbon 1 also, these are identical. So 3 and 3, 6 hydrogens are of one type. This methylene hydrogen is another type. So there are two types of hydrogens in this case. So two hydrogen types in this case in propene. Of course, in ethane there is only one hydrogen type. These 6 hydrogens are exactly the same. Obviously, these 4 hydrogens in methane are also the same. So this is one hydrogen type in methane, one hydrogen type in ethane, but two hydrogen types in propane. So therefore, there should be two products in this case, two chlorination products in this case. The first one is one of the 6 hydrogens is substituted, and the other is one of the 2 hydrogens, the methylene hydrogens, is substituted. So there are 2 products in this case, plus obviously HCl. These reactions, or this reaction overall, is called radical substitution because, as you see, one of the hydrogens in the alkane has been substituted by a halogen. So if you look at the 4 hydrogens in methane, one of these 4 hydrogens in methane has been substituted by chlorine. And one of the 6 hydrogens in ethane has been also substituted by chlorine, and the same thing here as well. It is a substitution reaction, so that's why it's described or termed radical substitution. It is also halogenation because methane has been halogenated. Yeah? Chloromethane is obtained from methane, so therefore it is a halogenation reaction. Let's now take butane and try to predict the radical chlorination of butane, again in continuation of our discussion of the radical substitution of alkanes or radical halogenation of alkanes in order to make alkyl halides. So this is butane. If we react butane with chlorine in the presence of light, before we write the products, we should think a little bit of the number of products that is expected in this case, and the number of products will depend on the number of the types of hydrogens. The butane has 2 hydrogen types. These 3 hydrogens on carbon 1, if you number this carbon 1, and the 3 hydrogens on carbon 4 would be the same. So these 6 hydrogens would be the same. So let's number it here. So 1, 2, 3, 4. So the hydrogens on carbon 1 and carbon 4 are exactly the same. The number of hydrogens in that case is 6, so this is 1 type. Carbons 2 and 3 are of a second type, if you like, or hydrogens on carbon 2 and carbon 3 are of a second type. So there are two hydrogens types in this case, and therefore we expect 2 chlorination products. One product would be obtained if one of the 6 hydrogens on the termini is substituted, and the other one would be if one of the methylenes or the hydrogen or one of these hydrogens on these 2 methylene groups is substituted. So we get 2 products. This would be one of them is one of the 6 termini hydrogens is substituted. This is the first product. The second product is one of the middle 4 hydrogens or the methylene hydrogens is substituted. So this is the second product. And experimentally, these 2 products are obtained in this ratio, so 30 to 70 experimentally. 30 to 70, chlorobutane is obtained in a 30 to 70 ratio to 2 chlorobutane in the chlorination reaction of butane that's induced by light. Now, if we take another example, and this other example involves isobutane, so isobutane can be chlorinated also under the same conditions. So isobutane plus chlorine in the presence of light, and again, before we commit to writing of the products, we should be able to think carefully about the number of products expected, and that will depend on the number of the hydrogen types. If you look at isobutane, if you number it here, so 1, 2, 3, you will see that 1, 3, and if you give this a star, 1, 3, and star are exactly the same. So 3 hydrogens on carbon 1, 3 hydrogens on carbon 3, and 3 hydrogens on carbon star. 9 hydrogens are of one type. These 9 hydrogens are identical, so that's one type. The second type is the lone hydrogen on carbon 2. There is only one hydrogen on carbon 2, but it's of a different type. So therefore, there are 2 types. Yeah, there are 2 hydrogen types in this case, and if there are 2 hydrogen types in this case, then we expect 2 chlorination products. 2 chlorination products are expected, and the first one would be, as you might expect, is one of the 9 hydrogens is substituted, and the other one is obtained when the lone hydrogen on carbon 2 is substituted. So 2 products in this case, and the ratio that is obtained is 35 in this case and 65 in this case. So these are the numbers, the relative numbers for the products obtained in these reactions. What can we learn from these numbers? Now, if you go back to the top example, the butane case, if you look at chlorobutane, this is chlorobutane. The relative amount of chlorobutane that's obtained is 30 to 70 relative to 2-chlorobutane. But chlorobutane is obtained by substituting 6 hydrogens. So 6 hydrogens contributed 30, if you like, 30%, if you like, of this compound. So 6 hydrogens gave 30. So what would be the contribution of a single hydrogen? Therefore, we should divide 30 by 6 to get the contribution of a single hydrogen, or the contribution of one hydrogen. So in this case, each hydrogen here contributed 30 by 6, and that is 5%. So we can say percent here, by the way, the percentages. Yeah? So 30% for the 6 hydrogens total. Each hydrogen then would contribute 5% if you divide 30 by the total number of hydrogens that have contributed to this yield. Yeah? So 30 by 6 is 5. Now, the methylene hydrogens, there are 4 of them. So 4 hydrogens gave 70. 4 hydrogens gave 70. So if we then divide 70 by 4, we get the contribution of each of these 4 hydrogens. So each hydrogen here contributed 70 by 4, and that is 17.5%. So 17.5% is the contribution of each of these hydrogens. And by the way, before we proceed, it's very important to remember that the hydrogens on carbon 4 and carbon 1 are primary, of course. Yeah, so these are primary hydrogens on carbon 1 and carbon 3. The hydrogens on carbon 2 and carbon 3, so these hydrogens are secondary hydrogens. Yeah, so the contribution of each primary hydrogen in this case is 5%. The contribution of each secondary hydrogen in this case is 17.5%. Let's now go to the second example, and the second example is chlera. This tertiary hydrogen, if we go back to the structure of isobutane, this is a hydrogen, and this hydrogen is labeled as a tertiary hydrogen, and there's only one of them. So this tertiary hydrogen contributed to 35% of the chlorination product. So the tertiary hydrogen, in this case, the tertiary hydrogen gave 35% of the chlorination product. So if you look at these numbers, the primary hydrogen contributed 5%, the secondary hydrogen contributed 17.5%, the tertiary hydrogen contributed 35%. What does this mean? What does this mean? This means that the tertiary hydrogen contributed the most. If the tertiary hydrogen contributed the most, it is therefore the most reactive. So this is the highest contribution. If it is the highest contribution, then it must have come from or originated from the highest reactivity. So that tertiary hydrogen gave the highest contribution, therefore it is of the highest reactivity, and the primary hydrogen accordingly would be of the lowest or the smallest contribution, and then the least reactivity. So the 5% would mean the smallest contribution, least reactivity, smallest contribution, or least reactivity, and of course the secondary hydrogen will be in the middle. So the primary hydrogen gave the smallest yield, therefore the smallest contribution, and therefore that is considered to be the least reactivity. On the other hand, the tertiary hydrogen gave the highest contribution or the most contribution, and therefore that could be attributed to the highest reactivity. So this is an observation or analysis of the numbers, okay, that are given, that are provided to us, but there has to be an explanation. And the explanation for this is due to the bond dissociation energy and also the stability of the intermediates involved in these reactions, yeah? Okay, now, in general, a tertiary hydrogen is weaker than a secondary hydrogen, which is in turn weaker than a primary hydrogen. So this is a tertiary hydrogen. This would be a secondary hydrogen, and this would be a primary hydrogen. We can label them. This is a tertiary hydrogen, secondary hydrogen in this case, and a primary hydrogen in this case. The bond dissociation energy for the tertiary hydrogen is 98 kilocal per mole. 96 actually, 96 kilocal per mole. 96 kilocal per mole is the bond dissociation energy of that tertiary hydrogen in this general structure. For the secondary hydrogen, it is 98 kilocal per mole. The bond dissociation energy for this secondary hydrogen is 98 kilocalories per mole. The bond dissociation energy for the primary hydrogen is 101 kilocal per mole. So therefore, the tertiary hydrogen or the CH, breaking this CH bond, or breaking a carbon tertiary hydrogen bond is the easiest in this case, which means this CH bond is the weakest. This is the weakest CH bond, and the secondary or the C primary hydrogen, this bond is the strongest. This is the strongest CH bond. This is the strongest CH bond because it takes more energy to break it or to dissociate it, as reflected by the highest or the largest bond dissociation energy. So this trend in reactivity, that the tertiary hydrogen is the most reactive, followed by the secondary hydrogen, followed by the primary hydrogen, is due to the bond strength or the bond dissociation energies of the respective CH bonds. So this is one explanation, and this explanation is connected to the stability of the intermediates involved in this radical reaction. And if you recall, radical reactions involve radicals, right? Yeah. So this tertiary substrate, or if you like, this compound containing a tertiary hydrogen should give rise after breakage of the CH bond. And of course, when we say breakage of the CH bond, then we refer to the homolytic bond breakage. Homolytic bond breakage, which means formation of radicals. Yeah. Okay. So this will give this radical, which would be, of course, because that's a tertiary hydrogen, this radical would be described or labeled as a tertiary radical. So this would give the tertiary radical, and this secondary substrate would give this secondary radical, and this substrate would give this primary radical. So this is the tertiary radical. This is the secondary radical, whereas this one is the primary radical. Now, that CH bond in the first substrate on the left, that is the weakest bond. If that's the weakest bond, therefore the corresponding radical should be the most stable. That tertiary radical is greater in stability than the secondary radical, which in turn is greater in stability than the primary radical. This is due to the corresponding bond dissociation energies of the CH bond. So the tertiary radical is the most stable because it came from the weakest, if you like, it has been formed by breakage of the weakest CH bond. The primary radical is the least stable relatively. So this is the least stable relatively because it results from breakage of the strongest CH bond. Yeah. Okay. So to summarize or to see what take-home messages we can do here, or what message we can take home or learn from, is that the tertiary hydrogen is the most reactive in these types of reactions. Tertiary hydrogens are the most reactive because it gave the highest contribution. Yeah. Okay. Primary hydrogens are the least reactive because the primary hydrogen gave the least contribution in these types of reaction. And this trend in reactivity is explained in terms of bond dissociation energy, bond dissociation energies of the corresponding CH bonds, and also then accordingly the stability of the radicals involved. The CH bond or tertiary CH bond is the weakest, the primary CH bond is the strongest, tertiary radical is the most stable, the primary radical is the least stable, and the stability of the radicals can also be explained in similar ways to the stability of carbocations. So here then, again, to conclude now, tertiary hydrogens are the most reactive, whereas primary hydrogens are the least reactive, and this is due to the corresponding bond dissociation energies and then stability of the intermediate radicals.